The network parameter that's going to prove most useful to you in microwave analysis, and the one that you're going to come across most frequently if you pursue a career in microwave analysis, is going to be the scattering or S parameters. And these parameters are based on reflections of waves at impedance boundaries. So they're kind of based on transmission line theory. Before we get into them, I just want to talk about the reasons for the popularity of the use of the S parameters for microwave analysis. And the first is that the other methods just don't work particularly well. Voltage and current can become increasingly difficult to define and measure in RF circuits, especially if that circuit consists of multiple devices in some sort of network topology. As we saw previously in our lab experiments and T-line analysis, the voltage and the current in transmission line is dependent on physical length of the T-line, and so the voltage and current vary spatially along the T-line. Additionally, defining other parameter types usually requires the use of shorts and opens, which are extremely sensitive to location. We saw that by putting a length of T-line in front of short or open, we can change its effects on the circuit. In particular, it's pretty generally not practical to actually mount a connector close enough to a microwave lump device to actually be measuring the port voltages and currents without influencing them. Additionally, many active devices such as amplifiers, we couldn't even put a short or an open on it to determine some of these other parameters because it would cause the device to oscillate, may result in device failure, such things like that. So it turns out, though, that we've got this other technique, and that's at looking at these incident and these reflected waves. And these are a natural description for microwave structures. And these reflected waves are really going to be looking at terminations in a match condition. And we use a match condition because we can apply a match condition to a circuit. It's going to result in a reflection coefficient of 0. That's a unique, repeatable termination. It's also insensitive to length of the transmission line to the match load, so that the measurement can be made without the device being measured directly. It doesn't have to be directly connected to a port. I can put transmission line in there as long as ZS and Z0 and ZL and Z0 are all the same. And also a match load is just easier to achieve physically than a perfect short or open over a broad range of frequencies. We don't talk about shielded connectors and things like that, but it's just easier to make a match condition. And then the final reason, other than it's empirically easier to determine S parameters than it is on some of the other parameters, you can easily convert from S parameters to all other parameter types. There's really simple algebraic manipulations that you can do to do that. So that's how S parameters are, or why S parameters are utilized. I'm going to go through two explanations of S parameters. I'm going to go through the Matt Turner explanation of S parameters, which is kind of an informal, not completely accurate explanation, and then I'm going to go through the more formal explanation. So the method I like to use is the circuit representing a vector network analyzer. So we've got our test, our device under test. This is just whatever circuit element we're trying to determine the S parameters for. And then we've got port 1, which consists of a generator and a internal impedance of the generator, typically 50 ohms. And then we've got port 2, which has the same. And both of these ports are capable of both sourcing and measuring, right? So what we'll do is we'll connect the device under test to both ports using 50 ohm cables, right? Z0 cables. It doesn't have to be 50 ohms, but in most applications it will be. We just have to impedance match the cable to the generator impedance, whatever the input impedance and output impedance of the vector network analyzer is. So then what we'll do is we'll set up the vector network analyzer to inject a sinusoidal signal, which I'm calling N1, of some amplitude into the device under test on port 1. The test equipment is going to set the amplitude and phase of N1, and it is going to record the amplitude and phase of both out 1 and out 2. Out 1 is the reflected signal, and out 2 is the transmitted signal. In a separate experiment, using the right side of the vector network analyzer, using port 2, the VNA is going to inject a signal with magnitude and amplitude, and that's into the test. The test equipment then is going to again measure two signals. It's going to measure the reflected signal, which in this case is out 2, and it's going to measure its amplitude and phase, and it's going to measure the transmitted signal, which in this case is out 1, and again it's amplitude and phase. And the S-parameter matrix is a combination of these 4 basic measurements. From that description, we see that S11, the S11 parameter, is the relationship between the signal that is reflected back into port 1 when port 1 is the sending port, when the signal is injected into port 1. So it's the ratio of out 1 to in 1 when port 1 is the sending port. S21 is the ratio of the transmitted signal to the input signal when port 1 is when it's the sending port. So those are S11 and S21. And so we see there that the first number here indicates which port is the output port and which port is the input port for the particular measurement. The other 2 S parameters are the same situation, just for when the transmitting port is port 2 here. So S12 is when in 2 is the input signal, well, how much power makes it through the circuit to out 1, and then S22 is when in 2 is turned on and port 2 is the transmitting port, how much power gets reflected back into port 2. So that's kind of the non-scientific explanation of what these S parameters are. Now let's talk more about incident and reflected waves. So this is the circuit that's typically used to explain the function of the S parameters. So as I said earlier, S parameters define a 2-port device using forward incident and reflected waves at both ports. So we've got this incident wave and we've got this reflected wave, and that's at port 1, and we've got this incident wave and that reflected wave at port 2. So for example, V1 plus is the voltage wave entering port 1. So what's happening here? Well, some of V1 plus will be reflected at port 1, which is going to contribute to the voltage of the wave exiting port 1, which is V1 minus. Some of V1 plus is going to get transmitted out into port 2, and it's going to contribute to V2 minus, right? So V1 comes in, some of it makes it through, some of it gets reflected. Of this portion that gets transmitted, of this V2 minus portion, it's going to hit this load, right? And there's an impedance boundary there. Some of this is going to get reflected back, and it's going to enter port 2 as V2 plus. Of this V2 plus, some is reflected, contributing to V2 minus, and some is transmitted, contributing to V1 minus. So from that description, we see that V1 minus consists of the portion of V1 plus that is reflected, along with the portion of V2 plus that is transmitted. So in terms of scattering parameters, we can write an equation, and we say V1 minus is equal to S11 times V1 plus S12 times V2 plus. We can write a similar equation for V2 minus, and that is S21 times V1 plus S22 times V2 plus. And so these are the scattering parameter equations, and they're often just written in matrix form as V1 minus over V2 minus is equal to the S parameter matrix S11, S12, S21, and S22 times the incident voltage waveforms V1 plus and V2 plus. We can see from this matrix description that the definitions of the individual S parameters are a fraction of the voltage wave that enters a port J, that exits at port I. So i.e. S11 represents how much of a voltage wave entering port 1 exits at port 1. So if we apply that to each of the ports, we get the following definitions for all of the port parameters. We have the S11 parameter is equal to V1 minus over V1 plus under the test condition that V2 plus is equal to 0. And this is, for this reason, this is often called the input reflection coefficient. S21 from that same definition is equal to V2 minus over V1 plus evaluated at V2 plus is equal to 0. And this is called the forward voltage gain. It's the gain from port 1 to port 2. Let's look at the other two S parameters. S12 is equal to V1 minus to V2 plus evaluated under the condition that port 2 is the sending port, so V1 plus is equal to 0. This is called the reverse voltage gain. And then the last port parameter, the fourth one, is the S22 parameter, and that is the voltage reflected from port 2 to the incident voltage at port 2 under the condition that V1 plus is equal to 0. And this is called the output reflection coefficient. So what this is saying is that the S11 parameter is equal to the reflection coefficient at the load. Oh, no, it's the reflection coefficient at the source, and S22 is the reflection coefficient at the load. The S parameters can be, since this is a phase and angle and this is a phase and angle, they're technically complex numbers. Right? It's got a voltage and an angle divided by a voltage and an angle, so I get, another voltage and an angle. And they're technically complex numbers, so you can report them with a real and imaginary part, or you can report them in logarithmic units in dB plus whatever the phase is. So to do that, you would just take 20 log of this magnitude that you get. So that's what the VNA does, is it takes 20 log. And typically when we refer to forward voltage gain and reverse voltage gain, we're taking 20 log of the magnitude of S21. And here we're taking 20 log of the magnitude of S12. So typically forward voltage gain and reverse voltage gain are usually in dB, and we usually ignore the phase when we're talking about voltage gains there. So that's the derivation of the S parameters.